выйдет, то нажать надо снова на фланаж. Вот все. Давайте дальше.
Зачем Станислав, если правильно штуку нажимать?
А?
Эту штуку рано нужно нажимать?
Ну, типа, если случайно не закрылось, нужно закрыть, то нужно вот так вот просто вот эту штуку выдвинуть. Вот эта фигня, она сетевая.
Супер, спасибо.
Да.
А вы ничего не знаете?
Поставь. Можно
Да. А что вы еще взяли?
А?
Что вы еще взяли?
Но я еще там окончательно не выбрал. Так, что я там взял? Так, из низ, вроде там тут не коммутативный диаметр, по-моему. Так, что еще из низов? Так, ладно, из курсов. Там это вот особенности комплексные.
О, гусеница.
Да.
Гусеница.
Да, кстати, да. Если проще, надо просто взять, потому что...
А вы только вышли забирали?
Да, это только вышли. Да. Что, может, порекомендовать что-то из других?
Ну, я не знаю, смотря, не знаю, просто может слишком взрослый, может, там интересно, но вот там Фонарева будет курс про конечномерной алгебры.
А, да, ну, я там, думаю, уже все знаю.
И у Юры будет семинар по операционной геометрии.
Вот это сейчас это вместе?
А?
Где операционная геометрия?
Глянь, программа минимальных моделей будет.
Ну да, это мне просто тоже, наверное.
С Орловым Шрамом.
Ну да,
Ну,
да.
еще Горчицкого есть семинар, но там вы знаете, там будет просто теория поликлассов проходить.
Надо подумать. Да, сейчас
Они вот весь прошлый год проходили теорию поликлассов 1, в этом году будут проходить теорию поликлассов 2. У них план такой.
И про что там у вас было до тех пор?
А я туда не ходил, но там прошли они, ну, там группу классов, Адели, Идели, вот это вот все.
Нормально. Да, что я там еще взял? Те автоморфные формы, это вот, которые Гриценко. Вот, так, не знаю, я понимаю, тут брать их нет, но, скорее, с вашим предложением я его не возьму. Это топологический анализ данных, чисто для расширения производства. Не знаю. Так, еще академическое письмо на английском.
А разве это кредиты?
Нет, так просто так для себя. К3 поверхности. Потому что я с ними, как говорится, не очень. Что может так где-нибудь теорию минимальных многообразий. Опять же, думаю, если либо придержусь. Да, все будет сходить, да.
Ого, это кто считает? Медведев, да?
Да, Медведев. Вот, да. Так, навесной я думаю взять это вот исчисление Гудвилля Горинова.
О, я про это слышал на Сударе только.
Так, теория представлений 2, наверное, возьму. Это, который Фейдмана. Так, не знаю, думали брать современные динамические системы, Скрипчика и Ландо. Это же расширение. Никогда еще не ходил туда на подобные курсы.
Но обычные системы вы знаете, да?
Я даже знаю, что это вообще за область такая, чем она занимается. Это я даже не ответить на ваш вопрос.
Ну, там, не, все знают, вот там есть система, она рассматривается эволюцию с течением исхода времени, и все.
Что-то похоже на дифференциальное уравнение.
Ну,
так,
это, я понимаю, очень важный инструмент.
Да, да, важный инструмент.
Вот Тимури нам рассказывал, наверное...
Да, конечно, там больше, с размерами, там тоже там...
Да, вот Тимур рассказывал у Валерия Лунца про комплексную динамику. Там время дискретно, там очень просто, там берется функция, скажем, на c целая, берется точка и применяется бесконечно число раз. И смотрит, что происходит. Куда эта точка убегает.
Да, кажется, он тоже, да, тоже сказал, что тоже на семинаре вычисления ты тоже довольно.
Да, наверное,
да. Когда уходит, конечно, говорят, нет. Да. Привет. Еще, наверное, как раз, наверное, помню, площадь динамики, по-моему, что-то там в категориях есть то же самое. То есть, если, например, производная категория, если там комплекс, вот смотрите на его длину в гомологиях, как нулевые, начните применять какую-то функцию. Применяете, получается такой, ну, после некоторых подкруток, там, на пределы взять, там все такое, взять какой-то интересный такой же инвариант. Там, по-моему, размер СССР, что такое. Она тоже динамика есть такая. Конечно, светненькая. И, конечно, немножко такая облачная, но все же.
Здравствуйте. Меня рассказать вам, как пользоваться доской, или вы знаете?
Нет, ничего не знаю, ничего не умею.
Мне сказали вас сказать. Она вроде проще, как бы, до этого. Вот писать skills. Вот. Силогический вот, если это сразу все. А еще можно стирать кусками. Для этого нужно для таких в ладони и... Вот, где работать? Да, вот погоди.
А вот эта кнопка может что строится?
Все сразу.
Сразу?
Да.
От начала лекции до конца.
А ее даже, по-моему, это, видите, рабочий стол. То есть я думаю, что нельзя будет сверху.
А, то есть мне придется на самом деле с нее стирать.
Да.
А, ну,
То есть прям как обычная доска.
то есть это означает, что всякие там PDF в конце лекции я смогу сохранить?
Надо полагать нас. Насчет теоретически будешь, наверное, свой эпизод программы, я думаю, на лекции.
Я пользовался как-то на дистанциации, там что-то я очень хорошо.
Ну, не станешь.
Так, а трансляцию мне надо запустить, да, и запись тоже.
Давай, я не знаю.
Ну, по крайней мере, сейчас мы про две доски видим. По времени не брали, начинать. Мои 10. Почти 10.
Закрывай покушай. Сколько подробно знакомиться с программой требуется на слушателя?
Я думаю, что очень понравится. То есть, знаете, насколько надо, производный фунт, который появился на столе, мне достаточно для ну, не сегодня, во второй половине увидел, как текущий аргумент, увидел, что будет надо. Вообще-то не очень много. Что, давайте начнем. Так. А вот мы записываем все телефоны, что все правильно включилось.
Все правильно включено.
То есть сейчас есть трансляция и запись я тоже включу.
Не, а запись она никуда не записывает.
А, то есть запись не останется.
Ну, трансляция останется на канале в виде записи после окончания.
То есть вот это вообще не даже не забыли.
Ну да, там что-то не подключено.
Okay. So let's start more some homological methods in commutative algebra. So I want to discuss some administrative matter. So first of all, I want to say what's the plan. So how can I change the color? I don't want this to be red.
Убрать надо что-то или?
No, I want black, not red.
Ага.
На перо, наверное, надо нажать. Или вот слева какой-то карандаш.
Что, кажется, черный.
Okay. So let me try again. Yeah, so what's the plan? So we're going to be several chapters. So the first chapter that we're going to start today is about regular sequences. And the notion of depth. And this is two basic tools in this whole course. But of course, in the first chapter, I'm not going to discuss only regular sequences and depth. There will be other sections about other stuff, so it will be a relatively long chapter. So then there will be a short chapter about going on Fourier modules and rings. So in general, there's not much you can say about this stuff, so it will be a short chapter. Now, 3 we're going to discuss Wallenstein rings. This is a special class of Cohen-Macaulay rings with kind of very nice duality properties, but to see why this is so interesting, so then I'm going to discuss more classical topics, such as regular rings. And complete intersections. And then in the chapter 5 we're going to study local homology. And there will be a local duality theorem, and you're going to see that Wallenstein rings are especially nice with this local duality. So these conditions will be also important when you study chapter 5 local duality. So essentially, these 4 chapters you can find in any reasonable commutative algebra text, for example, also one. So usually, if you just look at the Linus Moore's book, you'll see that the first 5 chapters is more or less that we're doing the basic commutative algebra course, and then this stuff is covered in the chapters 6 and 7. So I'm not going to follow precisely Linus Moore's, I'm going to use other books, I'm going to mention this later. But essentially, this is what is usually done in commutative algebra when you have enough time. For example, when you have lecture and half per week, then you can probably do standard stuff and also these 4 sections. Local homology is a different topic, so for this we need different textbook. And I hope that after this 5, which is necessary to understand the rest, I'm going to have time at least for one of the following 2 topics. I want to discuss Wallenstein homological algebra. And another possibility, big Cohen-Macaulay modules. So usually Cohen-Macaulay, for shortness, people say just CM, so big CM modules. So who of you know Hausmann-Husbaum formula? Hausmann-Husbaum formula. That's the right steps project. So we're going to do this today. So essentially the idea is that, and this is what we're going to do in the chapter 4, you can characterize regular rings. I hope you remember the definition of regular rings from the basic course. So that local material ring, which is regular, you can characterize them in terms of the modules. You can say that the ring is regular if and only every module has a finite projective dimension. That's the third theorem. Now, one of the basic starting points of the Bernstein homological algebra, instead of doing regular rings, you use Bernstein rings. And then you replace the notion of projective dimension by the so-called G dimension. And then you'll get the analogous theorem, which is now the Sayers theorem that says that the local material ring is Bernstein if and only if the G dimension of every module is finite. So you can, as you can see, that even to discuss this topic, well, we need to understand something about Bernstein, we need to understand Sayers theorem, so it's kind of not possible to go immediately to the interesting topics without covering the standard topics about classes of rings and homology. Yeah, and I also want to mention this, why the organization is as follows. So the first chapter is basic technical tools, but then in the commutative algebra, or in singularity theory, there is the basic classification of singularities. So we have regular rings, which means that we don't have a singularity. Then, say, R is regular. Then, of course, this implies that R is a complete intersection. So this is usually called CI for shortness. So complete intersection CI. Well, this complete intersection, it just means that I take a quotient by regular sequence. So wait, maybe 5 minutes, and I give a definition of a regular sequence. Then every complete intersection is in fact Wallenstein. And finally, every Wallenstein ring is Cohen-Macaulay. So this kind of 4 classes of singularities, or in other words, local non-trivial rings, that you can study in commutative algebra. Of course, you can study mobile singularities than this class, but at least in this classes there are quite a few interesting and helpful theories. Of course, some bad people can say instead of in mobile singularities, which are not going to call it, but this is not going to be done in this course. Yeah, so this is the plan. So cover some basic technical tools, then study this book. Well, essentially, I assume that you already know something about regular, but still here the most important result is the series theory. And for other classes we want to see other theorems. So study these 4 classes of rings, then see that this classes of rings are related with local homology, and finally see. So I mentioned what's the homological algebra. I want to say what's the big point of polymodules. Big just means that this is not finitely generated. So you can formulate condition for polymodule being polynomial and drop the assumption it's finitely generated. And why this is so important? Well, because in commutative algebra, during the 20th century commutative algebra, there were probably something like 10 or 15 conjectures, or sometimes more. There are summary conjectures, serial conjectures, open intersections, etc. And it turns out that the most important conjecture is the conjecture about the existence of a big polynomial. If you can prove this, you can derive every other homological conjecture. You can find that paper by Hofstad, is probably where this algebraic, so we can use the algebraics of the 20th century, several homological conjectures, and then you kind of give you a big picture why this is important. And for many years, people were trying to prove this existence of big polynomials, and now it is known. So it was proven in 2016. So, but of course, we're not going to discuss this proof. Essentially, what I want to show that if you know that there is a big polynomial module, then from this condition you can derive something else. And yeah, it was known for some nice classes of rings that this is true. For example, if you have something like local non-trivial rings, the local non-trivial ring such that the characteristic is 0 for P, and the residue field has the same characteristic, and then it's much easier to show that such model. Yeah, so this is the plan, and now I want to discuss what books I recommend. So for the standard stuff in the first 4 chapters, I already mentioned Homological book. So commutative ring theory. So the second book that I recommend is and Epson. For not poly rings. Okay, so this is for 1 to 4, for 5 homological homology. Well, there are several books, but probably as an introductory book, the first book of homology, the best one is by Younger and 6 other authors. So in fact, I think 6 or 7 authors of this book, and it is called 24 Hours of Homological Homology. So 22 hours mean that this is 24 lectures, one lecture is 1 hour. Yeah, and for the other topics, well, probably for the last one, there are no books, there are only papers. And for the 6, if you're going to do the 6, I'm going to give reference in the beginning of that chapter. Okay, so but you can start with these 3 books. Well, I think that the first 4 or 5 chapters are going to take at least up until November. So for the last, we think we get to December. So this will keep you busy for the next 3 months. Okay, so this is the plan, this is the literature, and about the grading scheme.
It's a different board, therefore you need.
Ah. Okay. The grading scheme is nice for you. We're going to have 4 assignments. So let me say it's 4 homeworks. Each assignment will be something like 10 up to 15 problems. So that depends how many problems I can come up for a given topic. So I hope I can do 15, but maybe it will be just 12 or 13 in some assignments. And each assignment problems. So each assignment is 25% of the course. And moreover, if you do any 10 problems, it will be 25%. So 4 assignments, so I'm going to give you something like 50, 60 problems during the semester. If you can solve 40, this is 100% for the course. So there are no midterms, there are no final exams, only assignments. So because I consider this kind of advanced course, and if you're taking this course, I assume that you can kind of organize yourself, so without any exams, learn what you want. So the reason why I'm going to give you 15 problems, because maybe in some problems, like in local homology, I'm going to offer you problems relating, say, local homology with algebraic geometry. If you don't know algebraic geometry, you can just ignore this and do the rest. Okay, so that's the grading scheme, the plan, another thing about the assignments. So the homeworks will be on the Google Class. So eventually I'm going to start a Google Class for this course and post assignments there, and you can submit assignments via the Google Class. That's what I usually do in my classes. Okay.
This homework on how much time?
Yeah, each homework will be for something like 2-3 weeks. So probably the first homework will be in 2 weeks. Because so far we don't know much to do the problems. Okay, so this is, I think this is all I want to say about the structure of the course. Any questions? Yeah.
Should we ask questions in English or we can in Russian?
Russian is fine.
It's fine.
Yeah.
Так. Можете напомнить ваше имя и отчество, пожалуйста?
Александр Борисович.
Спасибо.
Это все вопросы. Okay. So let's start the first chapter. Chapter 1, regular sequences. There is one more question I wanted to ask you, so let me finish the title. And depth. So the question is, so we have 2 hours every week. So do you want this to be 2 lectures, or do you want this to be a lecture plus a seminar? Well, because if you have 2 lectures, then they will definitely have time to cover some advanced topics. If you have only a lecture plus seminar, I'm not so sure. Maybe we will finish on just logical homology, but probably we'll learn the material a little bit better. So what I was thinking, maybe sometimes we're going to have 2 lectures and sometimes lecture plus seminars, so maybe half of the second hours will be seminars and half of the lectures. For example, today I planned 2 lectures because if we have just regular sequences, I don't know much problems about regular sequences, not for the seminar. So maybe, for example, today 2 lectures, next week lecture plus a seminar, we will do some problems on the depths.
That sounds great.
Okay, so
So will you sort of укладывать? Вы будете выкладывать задания или семинары в Google Classroom? это было очень удобно, потому
Well,
что
if you want, when I prepare problems, I can type them.
your course overlaps with some different courses, and therefore it's sometimes really hard to attend sooner. So
Sure. Well, at least when I prepare problems, I can take a photo and post it on again on the Google Classroom, so it's very same time, so I don't need to type. Okay. So first section of the first chapter is regular sequences, of course. So after you learn some basic commutative algebra, this is probably the most important, next most important notion in commutative algebra. So maybe before I even say the definition, let me say something about conventions. So perhaps I even need to say that first convention, then the first section. So what are my conventions in this course? So R is always, for me, associative commutative ring with the identity. So don't ask me again, all my rings always have one. Now, whenever I write M, I usually mean that M is an R module. If I forget to say so, when you see M, think about this as an R module. So sometimes I'm going to write pair R and M. And this is the standard notation for the local ring. First, with maximal ideal. So you need maximal ideal M. So my notation is standard almost everywhere. People use this. Okay, so this is local ring. What else do we use? Yeah, all ideals are proper, so whenever I write an ideal R, I assume that I is not equal to R, well, unless I say that I is the identity ideal or just ring. So probably this is enough for the beginning. Well, just to remember that, yeah, so maybe not the convention, but the standard kind of abbreviation. So when I say that this thing is L and R, I mean that this is local, Noetherian ring. So always L and R stands for local Noetherian ring. So we're going to start with some general rings, but slowly, step by step, we will end up with local Noetherian rings. So in commutative algebra, the most important case is the local case, and then we can reduce this to the local case. You do this, and if you cannot, well, that's a different question. It's usually quite hard. Okay, so the definition. So for an R module M. Now we have the following two parts in the definition. So first part you already probably know very well. So element little x in the ring R is called M regular. Another way to say this, regular on the module M, or another way to say this, non-zero divisor. And also for the zero divisor, I like to use just ZT, just for shortness, not to write this all the time. So this is not a zero divisor. Well, if you have the following the property that whenever you have x acting on some little m is 0, so m little m in the module m, this implies that the element is 0. So this is indeed just not the zero divisor on the module m. Yeah, and when I do this definition, well, you can also think about the case when the R module is just the ring itself. It's also quite important. So the second part of the definition, the generalization of the first part for the several elements. So a sequence of elements x1 up to x1 in the ring called an M sequence. Another terminology would be sequence which is regular on the module M, but M sequence is a little bit shorter. So if we have now two properties, so if, well, first, xi, so the definition is inductive. So xi is regular on the module which is quotient of the M by the submodule, which I obtain by looking at the ideal generated by all the previous elements in the sequence. So generate the ideal and take a product of the module and this ideal. So this is some submodule M, so this is a quotient module. So for example, x1 is just by definition regular on the given module M. M2 is regular on the quotient of the M by the x1 M, etc. So this is the first condition, and the second condition is that quotient of the module M by the submodule, which is a product of the ideal and the module, and ideal generated by the whole sequence up to the M, this is not zero. So a few remarks. So remark. First remark, this is about terminology. If only condition 1, so Robin 1 is required, then the sequence is called weak regular sequence. Two, in the situation of the local Noetherian ring, of course, 2 is satisfied.
Is it true if we take x1 to be units and the other one is just anything? It will be
Well,
sequence.
well, I want, of course, all my elements to be non-units.
No.
So, meaning not invertible in the ring R.
You specify how you specify anyhow that they are non-units if they are regular.
Well, what I meant is that when you do this in the applications, you usually assume this, but formally in the definition, well, you want to start with element 1.
Yeah, element 1 and then
And
everything.
well, element 1 is definitely a regular element.
Yeah.
Yeah, but then if you take a quotient by the element 1, right? So this, the next module will be just a 0 module. Yeah, and we have this assumption.
Is regular. Yes, until the weak.
Yeah, for weak this works. Yeah, and of course. Yeah, sure. You can consider that this case is when eventually on some step the quotient is 0, but of course this is always can be done as a remark. Of course the main interesting case and when you have this condition and all the quotients are non-zero. Yeah, so I want to say that the in local Noetherian rings condition 2 is satisfied always by Nakayama's lemma.
Why is the second one? Why is it true?
Well, that is because whenever I have a local Noetherian ring, since a local Noetherian ring, whenever I talk about the regular sequence, this has to be inside the maximal ideal. And usually it's not very interesting to just study all possible regular sequences. Usually the situation is the following. You have a ring, inside this ring you have an ideal, and inside this ideal you study regular sequence for the given module. So this is what we're going to see in the statements. That
Excuse me, but if we take x1 equal to 1, then...
Я не понял, если мы возьмем x1 равно 1, у нас же даже
локальным неутеровым кольце.
Что все необратимы.
well, here this is the assumption, so 1 is not in the maximal ideal.
Okay.
Yeah, and examples, so at the moment, we're not going to discuss very interesting examples, but of course, there is one trivial example where you take a ring to be polynomial ring. You can take also formal power series if you want. So R is a polynomial ring, and of course the sequence, and this is where I want to emphasize that I use different fonts. So the indeterminants X is a different font than the just elements. So when I have elements in this definition, I use this little x, but for the variables I use the capital X. So this is of course a regular sequence. Well, we can immediately see this. This is quite easy exercise, I would say, a trivial exercise. But the point is that actually, up to technical detail, every regular sequence is a sequence of this form. So this is what we're going to prove even today. This is one of the main theorems about this thing.
Yeah, and when you say regular sequence, you mean R regular.
Yeah, so of course, when I just say regular sequence, I assume that the somehow module is understood, and in this case, of course, the module is just the ring. Okay, so example 2 is more interesting. This is even an example/exercise. So in this case, I take R to be again a polynomial ring, but only on the 3 variables. And x1 is the product of the variable x times y minus 1. x2 is the just variable y, and x3 is the product of the z and y minus 1. So I think this is the first exercise that we're going to do in the seminar, probably next week. So the claim is that if you take sequence in the order as it is given, x1, x2, and x3, then this is regular, so say R regular. But if you change the order and consider x1, x3, x2, then this is not R regular. So as you can see from the definition, it doesn't follow that this notion doesn't depend on the permutation. And indeed, if you just consider the general case, this is indeed, if you change the order, then a regular sequence can become non-regular. So that's a problem, but usually this problem is fixed by going to the local rings. If I add additional brackets here, and this will be local ring, then this is a regular sequence and this is also a regular sequence. And the general statement we again we're going to prove as a theorem later today. Okay, so there are no questions from the definitions. I'm going to erase this. Let's see. Maybe before I prove our first statement, I want to say informally why this is an interesting notion. So the idea is that, well, if say x is R regular, then I hope you know the statement from the dimension theory of commutative rings, that the dimension of the quotient by a regular element is equal to the dimension of R minus 1. Do you know this?
And X is values. And X is values.
This is the regular.
Yeah, it's R regular.
Well, we assume it's not here.
Yeah. So let's say that regular element is a non-unit always.
about crude dimension.
Yeah, so this dimension here is the crude dimension of the ring. So you can see that we have just a regular element, and you quotient by this element, you drop the dimension by 1. So what you would expect that so this is not a formal statement, this is kind of expectation. So if you have a maximal regular sequence, then this n is actually the dimension of the ring, right? So you take a quotient by one element, you drop dimension by 1, take the next quotient, drop dimension by 1, until you reach dimension 0 and you don't have any regular elements. So there are rings when this is not true. But when this is true, this is exactly the rings that are called Homological. So we can introduce the notion of dimension in two ways, the proof dimension and dimension by inductive by on every step take a quotient by a regular element. And if these two notions of dimension coincide, this is a Homological. And the generalization for modules is quite straightforward. You need to say that the length of the maximal regular sequence on a module is the same as the dimension of the module, meaning the dimension of the support of the module.
Yeah, in the theory, there are Archimedes rings that have no regular elements.
Yeah. Okay, so this is kind of the announcement why this is an interesting and how this is related to the other chapters of this course. Okay, so maybe. So I was thinking maybe I want to say something else, but I don't remember the point. So maybe let's prove first proposition. So let M be an R module. So we have a sequence of the n elements in the R, which is weak M regular, or just M sequence. I probably should say that this is M sequence. With M sequence. Now suppose that the phi is a map from the ring R to some other ring S. So this is ring map. And M is an R flat S module. Maybe just a comment what I mean by this. It means that M is given as an S module. You can consider this as an R module by the restriction of scalars. As an R module, this is flat. Do I need to remind the definition of flat module? Okay. Do you have any questions? Because I'll stop me at any moment. Okay, so this is the assumption. So then, the conclusion is that this sequence of elements and also the sequence that I obtained by applying the map phi to this sequence these sequences are both weak M tensor N course over R sequences. So sometimes I'm going to do this in this course. I start with some proposition which is quite technical, and then after I prove the technical part, I'm going to give you some corollary or explanation why this is actually an interesting proposition. So let's first do the technical part.
So like phi x1, x pi xn, it's S, elements in S.
Yeah, so here when you look at this tensor product, since n is actually originally its S module, this tensor product can be considered as an S module.
Yes.
So if you wish, you can think about n as a bimodule, so it has R module structure given by this y, and also some given S module structure. So you can apply this sequence to this as an S module, and you can also think about this as an R module.
So we
Okay, and the proof is more or less up to some words. Just one simple observation: how xi is acting on this tensor product. So let me write the action on a simple tensor. Well, by the definition of tensor product, I can as well write it like this. Right? But now I want to move xi from the left to the right. So when I do this, what I'll get? Yeah, exactly. So this is the same as the phi of the xi. This is just the definition of the tensor product, right? When you have a scalar, you're supposed to move it from the first factor to the second factor, but of course you use the different actions on the modules. So here this is a given action, but the action of the element in the ring R on some S module is why this my phi. So hence there's nothing more than the definition of the tensor product of the modules. Okay. So if the action is actually by the xi and the phi of the xi is the same, so it is enough. So let me say hence it is enough to consider the sequence x1 and xn. Okay. Now, of course, it's important to understand one very simple thing. To say that they say element x1 is regular, I can as well say that the multiplication by this map x1 is injective. Right? So that's exactly the same property as being conservative divisor. So whenever I write this element as a map, it just means that I take an element little m and send this to the product of the x1 and m. Just multiplication on the given element. So this is injective, and this is being just equivalent to the definition of the x1 being regular on m. Okay. Now, next step. Well, maybe I use this and say that from this I can see that the tensor product of the m and n has a map which is a tensor product of maps. So multiplication by x1 tensor. Let me write n. Sometimes people use this notation. I just want to introduce this in the very beginning, just in case I forget that I really don't like this notation and use it for some reason. So if I write something like this, phi. Okay. I want to do this in general, but maybe let me just say what it means here. So whenever I write tensor product with the module, and this is supposed to be a map, this just means that instead of module, I use the identity of this module. Just one of the conventions. Okay. So this is injective. I claim that this map is also injective. Can you tell me why? Yeah, because n is flat, and it means that preserve exactness when you take a tensor product with this module. So this is injective. Since m is flat. But this map x1 tensor n is multiplication by x1 on the tensor product. So x1 is weak m tensor n regular. And then the rest of the proof is by induction. So we can notice that if you take a tensor product of the m and n and take a quotient by the x1 M tensor with N. Well, then this is isomorphic to the M x1M, then the product with N. Okay, so next question, why this isomorphism is true?
Well, it's just because x1 as an ideal of the M tensor N, it's the same as an ideal.
It's always true because the product is quite exact.
Yeah. And then in this case, this is flat, this is even exact. So you can think about this as follows. You have M, this is multiplication by x1, M here, this is the quotient, right? You always have this short exact sequence. And considering such short exact sequences is crucial step in many arguments. So you take the short exact sequence and take the tensor product with N, and you get this.
And here it's not important that N is flat here.
For this thing?
Yeah.
Yeah, I think the right exactness is enough. Yeah, so then you use induction. Finish by induction. So you can see that the definition of regular sequence is inductive definition. So it is not a surprise that in many proofs, especially in the easy proofs, induction is also works quite well. No matter how to try the point. Okay. So now why this is interesting, and for us the main application will be the following corollary. So we take local Noetherian ring. So M is finite R module. So we have a sequence. So this is M sequence. And now suppose that we have prime ideal P in the support of this module M. You remember still what the support of the module is. So this is all the prime ideals such that the localization in those prime ideals is not zero. So then, take this prime ideal in the support and assume that the sequence that we consider is actually a sequence of elements in this prime ideal P. So then, this sequence as sequence in the localization RP is an M sequence. So it is an MP sequence. So in other words, you can localize regular sequences going up to this assumption that you consider the regular sequence inside the prime ideal in which you localize. Okay, so the proof is quite easy. The key observation that if you have a map to the localization, right? So this is standard map that sends X. However, not necessarily localization of prime ideal, any localization, that any such map to the localization is a flat map. So in other words, this ring RP is a flat as an R module. And then, since localization of the MP is non-zero, or this we assume by saying that the P is in the support of M. So by Nakayama's lemma, we can say that the MP is not the same as PMP. well, hence this is MP sequence. So let me just comment about this proof. So the fact this is a weak regular sequence, I already have from the previous proposition. I don't really need to say anything about this. So the point is that in this statement, I don't have assumption this is weak. This is just an M sequence. And for this, I need to say that. Well, I need to say that if I take an ideal generated by this sequence and take a product with the MP, well, this is definitely is contained in the PMP, right? But by Nakayama's lemma, this is also a submodule which is strictly smaller than MP. Hence, this thing cannot coincide with the MP. So this is not just a weak sequence, it's actually an MP sequence.
So why do you need R to be LNR?
Well, that's a good question. Probably I don't really need this. Well, the argument works, yeah, for any ring.
Well, why do you
I know. Well, I need Nakayama's lemma.
Yeah, we kind of need it because it doesn't turn. Oh no, we have it because
No, yeah.
the localization doesn't turn our factor module, quotient module into 0.
Yeah, but this is we suppose here.
Yes, in support.
Ну, не очень
Support.
Yeah. So the reason why
Declaration. О том, что вот, может пользоваться в носителе M, может он не лежит носителе M фактор по смыслу.
Yeah, okay. So anyway, so the statement for the local Noetherian ring is true, but you can think about the generalizations. Well, so maybe I should raise this.
So, неутилированность нужна или нет?
Sure.
Я Накаяма не нужна.
Алкалис зачем тогда?
Накаяма не нужна. Чем Накаяма смотрит?
Well,
Нужно все, нужно инициировать локальность, потому что лемма Накаяма так в случае с локальностью кольцом.
yeah, but we'll use Nakayama's lemma for the localization.
Говорили, когда мы используем.
So this is Nakayama's lemma for this ring.
Я понял, да, вот так.
Да, вот это есть.
Ну, да, это правда.
Okay, so it looks like actually we can drop that this is local. If we just take R Noetherian and all the other assumptions, I think this proof works. Yeah, but so let me erase this. So next proposition. Sorry, proposition. So as before, M is our module. We have a sequence, which is a weak sequence. Yeah, of course, if you want to go from the weak sequences to the just M sequences, for example, in the first proposition, you just need to additionally add the condition that the sequence of the tensor product satisfy condition 2 from the definition. So there's not really proof, you can just add additional condition 2 by hand. Okay, so now I want to assume that this is again a weak M sequence. So it is a weak M sequence. Well, this is actually the first homological kind of statement, and it's a little bit surprising. I remember I was quite surprised when I first saw this statement. So if sequence, unfortunately, the word sequence I'm now going to use in two different meanings. So that as a sequence of elements, and also the sequence of the modules and maps, or in other words, complex. So this is so let me call this 1. So this sequence of modules is exact. So if then the sequence 2, which is just obtained by the reduction modulo regular sequence, and the reduction means that I take a quotient by the ideal generated by this sequence. So for the maps I'm going to use phi 2 bar, phi 1 bar, phi 0 bar. And I just want to say again, this is quite standard in algebra. When you consider something modulo ideal, or just modulo element, use bar for the quotient object. So on some commutative algebra seminar, I would write phi bar and 2 bar and 1 bar and 0 bar, and everybody would understand that this is a quotient by this sequence. Okay, so then this sequence, of course, the statement is that this second sequence 2 is also exempt.
And the first sequence is, it has something, and 3 and 4 and so on, or is it just 3 of them?
Just well, actually 4 of them.
Yeah, so it's not like a resolution or something.
Well, you can think about this as a kind of the first steps, first 2 steps in the resolution.
Yeah.
But well, I don't assume this is some free or projective or flat, just any modules. So what's surprising about this statement? Well, of course, you can observe immediately that sequence 2, let me write this a little bit in formula, I think it's not hard to understand, that the sequence 2 is obtained from the sequence 1 by taking the tensor product with this quotient ring. Right. This is exactly what I have here. So by definition, the maps that I have here is just the maps that I obtain from such tensor products. But of course, we know that the tensor product is right exact. So the exactness at this term is not a surprise. And the exactness at this term. So let me write this, that since tensor product is right exact, we only need to check exactness well, and the term n1 quotient by the ideal generated by the sequence times n1. Use exactness at the n0, and m follows from the general properties of the tensor product. Okay, and this is the surprising part, right? So if I just drop n2, it will be just some automatic consequences of the standard theorems of homological algebra, but there is an additional exactness which is not immediately clear just from the general abstract picture. Let's do this by hands. So let's say that phi 1 bar on some element y bar, again, y bar is just a class in the corresponding quotient module, is equal to 0. So this means if I go back to the original sequence, that the phi 1 applied to y, so y is just an element in the, so y lives in the N1, and the class of y give me some element in this quotient. So this means that the phi1 applied to y is the product of the x and z. Yeah, so I need to say that I skip this step. So the proof is of course by induction. So by induction on n, and of course it's enough to just consider case when n is equal to 1, and x is the same thing as the x1. So I'm doing the case when n is equal to 1, and of course the general case is exactly the same. You can do this by induction step by step. Okay, so phi1 of the y is xz, so where z is some element in the n0. Okay, so then x phi 0 z is equal to 0. And why this is so? By the way, phi 0 is a map here. Do you see why this is true?
Because of exactness.
Yeah, exactly. Because if I apply phi 1 and then I apply phi 0, I'll get 0. And here I just apply phi 0 to the product x and z, which is phi 1 of something. So just by the, not really just by the induction, by the exactness, but just by the fact that this is a complex. Okay, but now phi 0 is an element in M, and x is regular on M. So I can as well say that actually phi 0 of z is equal to 0. So if the phi 0 of z that lives in the n0 is 0, and now I use the exactness, it means that the z is phi 1 of something. So let me just say that the z is phi 1 of some element, let me call this y prime. Now if you do this very simple computation and compute what phi 1 is doing on the difference y minus x y prime, then you'll see that this is 0. This is 0. So in other words, since this is 0, we can say that y minus x y prime, well, this, if phi 1 is mapping this to the 0, and now we use exactness in the next element in sequence in the n1, so this is phi 2 of some element in the n2. Well, let me not specify this element and just write that this is here, so this is element in the phi 2 of the n2. Okay. Finally, I take this last inclusion and reduce this modulo x. Then I'll get that the y bar is in the element phi 2 bar n2. Well, I can write n2, I can write n2 modulo this x1 that I extend n2, it will be the same thing. So we proved what we want just by some direct computation. So additional exactness at this term. So that was some technical statement.
What is the main reason behind this statement? Why do we have exactness in this case?
You mean not just a proof, but some conceptual explanation? Well, I'm not sure that I have one.
Yeah, one small, like, if it will be some resolution of n by, well, it will be infinite to the left, after tensing with r factor x1, xn, it could be not exact.
Well, this is exactly what I wanted to say next. So this is kind of, again, technical part. And now let's derive an interesting part from the technical part. So next proposition. So I can formulate this a little bit more general, just the resolution. So let me say that n, say with the lowest low bullet is a complex. So it unbounded on the left. So that nm, let's say by m, and m minus 1, by m minus 1, and 0. And let me call this last term n to the negative 1. So, of course, we can think about this as an augmentation of the corresponding resolution. A little bit more general situation is just the resolution of the n negative 1 by this time. So let this thing be a cyclic chain complex. Complex, sorry, of our modules. Our modules. If we have a sequence, so which is weak. Weakly Ni regular. So you can see that actually in this proposition I require much more. So here I only ask this to be weakly regular on the M. Here this is on every term. But this is usually not a problem because, well, in many situations, well, you use, for example, you choose a free resolution, and you can choose a sequence which is regular on a given module, which is n minus 1, n with index minus 1, and also regular on the ring itself, hence it is regular on any free module. So it's still quite useful in applications, despite this huge assumption that it's weakly regular on every ni. So this is for any I, starting with minus 1. So then the product of this complex with the R module of the sequence is exact. The proof is as before by induction. And it's as in the previous proof, it's enough to consider n equal to 1 and x1 to be identically, or n x1 to be exactly the same thing as x. So this x is an I regular for any I. But if this is an I regular for any I, in particular, this is regular on the submodule. So I can conclude that xi is regular on the submodule, which is the image of the phi with the index I plus 1. I hope this is correct. Yeah, so regular on this thing. So we apply previous proposition to the following sequence with 4 terms. We have ni plus 3, which is mapped to the ni plus 2, ni plus 1, and finally image of the phi I plus 1. And if you do this, you'll finish the proof. Do you agree with that? Because, well, we have exactness definitely here and here, just by the right exactness of the tensor product, and then just we do this step by step. So here, for example, you always get exactness here. So we'll get additional exactness at the N1, then we do the next step at the N2, etc. And then we get exactness everywhere. Okay, this was kind of easy propositions, and maybe it's not so clear. Well, maybe the last one is clear why this is useful. We're going to use this.
Why does the proposition hold below the I still? The last proposition.
No, but here I can choose any I. This is true for any I.
Ah.
Okay, so now it looks like I have 10 minutes. Well, maybe I'll start the proof and continue the proof after the break. So the fundamental theorem, probably the most important theorem, well, at least for me, are the regular sequences. So this is the theorem by Rees. This is one of the founding fathers of this area, homological methods, or even just thinking about commutative rings in terms of modules of these commutative rings. So it was Rees, Serre, and Algebra in the late 50s, who introduced the main objects and theorems in this area. So let x1 xn be an M sequence. Of course, as before, M is an R module. We're not going to say this. Ideal I is an ideal generated by this sequence. Now F is a polynomial with coefficients in the module. Have you seen these examples before? So it means that, well, you have n variables as before, but the coefficients is just no elements in the ring, but elements in the module. So this is some new R module.
Що значить буква FG?
So this is not FG, this is F is an element. So unfortunately on this electronic whiteboards, my handwriting is even worse than the chalk. Okay, so this is a polynomial. So this is homogeneous, so this is homogeneous of some degree d. So if we have the following assumption, I take this polynomial, compute this polynomial on the regular sequence. Again, notice the difference between two forms for the variables and for the elements in the sequence. So if when I compute this polynomial, I get an element in the I to the d plus 1m. Then
So is it this polynomial the same as tensor in M with the polynomial ring over R?
yeah, let me just write this. You can think about it just naively as a polynomials with coefficients in M, as I said, but of course the following observation is also true, that this module that I just introduced is exactly the same thing as the tensor product of the module over R with the polynomial ring. Yeah, so if the value of this polynomial in the given regular sequence is in the ID plus 1m, so then the coefficients of F are in IM. Again, this kind of technical part of this theorem, we're going to prove it first, and then after the proof, we're going to see why this is actually a very interesting interpretation, which is much easier to understand and remember. This will be this theorem is the answer. Remember that in the beginning I said that essentially every regular sequence is like a sequence in the polynomial ring. So this theorem give you a very concrete answer to this question why exactly this works. Okay, so proof is actually kind of complicated, and I want to say this is not kind of common proof from homological from the point of view of homological methods and algebra. It's kind of separate proof, separate ideas. It's more or less elementary, more or less computations of polynomials, but it requires several steps. So first of all, of course, we're going to prove this by induction on n. But induction on n will be not very straightforward. Well, first, maybe it's even interesting to consider the case when n is equal to 1, the base of the induction. So in this case, the polynomial f is some element in the module m, the coefficient, and then have x1 to the d. Right? So the homogeneous polynomial degree d in one variable, this is the only option. Okay, now the assumption is that the m, when I compute this on the x1, right, so this will be m product x1 to the d. This is an element in the module which is the product of the ideal I to the d plus 1 and m. Well, in terms of elements, we can just write this equivalently that the product of the m x1 to the d is equal to the m tilde, well, some other element, and x1 to the d plus 1. So of course, m tilde is again just some another element in the m. So in other words, I can rewrite the last identity as the product of the m minus m tilde x1, and then I have a product. Sorry, this is the wrong font. So this is x1 to the d. Well, so this difference is an element in the m, right? x1 is regular on the m. So I can do this kind of step by induction. I can drop one x1, then x1 squared, x1 cubed, etc. And by the regularity, so x1 regular, I can say that the m, m is equal to the m to the. But that's exactly what I want, right? This is the coefficient, the only coefficient in my polynomial, and this coefficient is exactly of the form that I have in the theorem I am. Okay, so now let's do the step of the induction. So suppose the theorem is true for n minus 1. I want to show that this is true for the n. And let me now also introduce another issue. So set ideal J to be ideal generated by the x1 xn minus 1. Okay, so the step of the induction I want to separate into 3 steps. But okay, maybe according to this clock I have 5 minutes, so maybe I can do the first step. So step 1. And in this step 1 I'm going to show that the xn is regular on the quotient module m modulo j to the lm. So this is for any l greater or equal than 1. Okay. So the proof for this step is again by induction. By induction on l. So now I'm doing this induction just for this step 1. And separately prove this step 1. Now, of course, the base of the induction when L is equal to 1 is clear. Right? That is because we'll just a quotient by J, and this is just a definition of the xn being regular on the Jm, or on the quotient by Jm. Okay, now let's take some positive. Not positive, but greater than 1. So let's assume that xn times some m is an element in the j to the lm. So I want to say that the product is 0 in this quotient module, but I can currently formulate this property, right? Now, of course, the goal is to show, so what I want to show.
Here's the question: do we need the homogeneity
What?
of the polynomial?
F?
Yeah.
Sure.
I mean, couldn't we just decompose it into homogeneous components, and then if we proved it for the higher, I mean, would it work out?
The conditions depends on P, on degree.
Yeah, but if this is satisfied for some big events, it's satisfied for all smaller things, right? Vice versa, but you get the idea.
Yeah, I think you can do this, but
Нет,
Well-
но чтобы степень не была равна d. Если ты сказал, что после этого коэффициенты лежат
Не, ну, степень
и
это
пишут,
будет.
может, давай у вас то же самое.
Степень-то будет, да, просто там еще какая-то сумма из одного homogeneous части, которая степени d, потом homogeneous часть, которая поменьше степени, поменьше и так далее.
sure, but it looks like you require for the main part you get this condition as before, and then for say the plus and something called degree say d minus 1, you still require this condition, right?
Right.
But well.
Okay, and then
that's-
chance
Yeah, but for me it's not very interesting because after this theorem I'm going to give you reinterpretation, and for the reinterpretation that I was mentioned easier to understand and remember, the homogeneous is definitely enough. Okay, so I want to finish this first step before the break. So I want to show what the goal of this argument is to show that m is in the j to the l times module m. So I'm just kind of, for this particular model, I wrote the condition that xn being is regular. Okay. But by induction, we have that m is then the j to the l minus 1 m. Right? So I'm doing this step of the induction. I assume that I know the statement for the l minus 1. I want to show this that this is true for l. Well, if I have this last property, I can write m as some polynomial g on the regular sequence.
So what do you know by induction? Like, we know that if x and m lies in jl minus 1m, then m lies in jl minus 1m. But why x and m lies in jl?
Well, I'm proving this statement by induction of L.
Yes.
So I'm doing this step with the induction. So I assume I know this for the L minus 1.
Yes.
So I want to show that this is true for the L.
Yeah, I understand.
So this is what I'm doing. So if I have that this is true, this is definitely true for the JL minus 1. Hence I have this inclusion. So what I need to show this is true for L minus 1. So now I want to write M as a polynomial. Right, so this is just because if I look at this last result, this element M is a polynomial, so let's call this polynomial G on the regular sequence. Sorry, but this is not N, this is N minus 1. It's N minus 1. And this is homogeneous of degree L minus 1. L minus 1. Now let's set G tilde to be xn times G, another polynomial, and apply theorem to the G tilde. Right, so since this polynomial g only depends on the n minus 1 variable, by the step on deduction, I can assume that this theorem is true for the n minus 1. So I apply this to the g tilde. So from this, I can conclude that the coefficients of the g tilde are in the Jm. So finally, if the coefficients of the g tilde are in the Jm, and g tilde is just the product of the xn and g, and this thing is regular, so then coefficients of the g are in the Jm. But now we just look at this formula again, and if the coefficients of this, well, actually we'll look at this formula again, and if the coefficients are in the Jm, then the m is in the j to the lm. And this is the end of the proof of this step. So let's take a break.
Хотите, что-то запись смещает m, умножает x m в m или большой?
Sure. Of course, the m is here.
Почему m выглядит как
Oh,
Сейчас
this,
g от x равно x минус q не в m лежит.
well,
Многочлен с коэффициентами в m.
Вообще коэффициент все.
yeah, so let me write that g is in the m in variables x1 up to xn minus 1.
Каким образом мы применяем теорему g с волной?
Well, the statement is that if we have this, right, and for this polynomial this is true, then we can say, well, the fact that this is, well, d could be anything, right? So the only important part is that this is the degree of d plus 1 here. Let me now check this. Is this true?
Да, там будет L, да? Он же будет лежать xn m, он лежит в GL.
Right, so this is a polynomial in the variables up to n minus 1, so the degree is L, and
А мы рассматриваем его как многочлен от n-1 переменной.
yep,
G с волной.
yep. So that's the point. So well, applying the theorem, but for n minus 1 variables. So to prove that, to do the step of the induction, I do additional induction here, and here I use the theorem for n minus 1. Yeah, but now indeed, let me check that everything correct with the degrees. So this is homogeneous of degree L minus 1, right? So yeah, sure. And then, so this is of degree L minus 1, right? But then I multiply this by the xn, so it will be of degree L.
No, we have degree L minus 1 потому что мы рассматриваем это как многочлен от n-1 переменной, а xn у нас сейчас не переменная. Это останется многочленом в степени L-1.
No. I can look at this polynomial and as a polynomial of degree L. For
We cannot apply
Нет, да,
theory.
ну, это правда, мы не можем так делать, потому что тогда у нас переменных будет n станет. Если мы его рассматриваем как многочлен в degree, в степени L, после умножения.
Сейчас вы меня путаете. Здесь
Нет,
переменных n-1.
да.
С этим проблем нет. Теперь...
После умножения x у нас не увеличивается степень. Потому что x не переменная.
Да, это просто элемент кольца. Да.
Вот, значит, g с волной это все еще в степени L-1.
Да.
И он лежит в GLM, тогда можем использовать шаг индукции.
Да. Все так.
Все хорошо.
Но мы доказали, что коэффициенты G с волной лежат в JM.
Нет, коэффициенты лежат в JM. Это заключение теоремы, да, только здесь...
Да, и что теперь?
Да, а теперь мы замечаем, посмотрите, вот у вас, вы хотите понять какой-нибудь коэффициент вот этой штуки, да, он устроен как x в степени n на какой-то коэффициент из g. Да. Ну, соответственно, просто примените регулярность, да, и заключите, что на самом деле вот это C, оно тоже находится в JM. Ну, как, если вот этот коэффициент, который для just волной, да, он у нас находится где? Он находится вот здесь, правда же? Да. Но теперь вот эта штука, она здесь регулярная, ну, потому что это вот последний шаг в определении будет. Ну, соответственно, если она регулярная, ну, тогда можно ее просто взять и убрать и сказать, что отсюда следует, что C, да, это уже, а C это был какой-то коэффициент уже, чего он был, вот уже. Давайте все-таки сделаем еще тоже вот последняя редакция. Он находится вот в таком,
Прикольно. Да.
Я когда вчера что раз это приходит китайцы. Ты видел повестку? Так это...
Хорошо, хорошо, мама настроение, я не сказала.
Начинается очень...
Когда
Можно спросить, вот тут говорили про лемму Накаямы, что там нужна нётеровость.
Не, вроде не знаю.
Не, в принципе, глобально в лемме Накаямы же нётеровость не присутствует.
Да, вроде у нас сохраняется локализация, поэтому там не нужна
То есть там вообще не
Можно
локализация,
еще спросить, вот не очень было понятно, когда вы вначале говорили про что-то классификацию сингулярности. Можете повторить по-русски этот момент, пожалуйста?
Ну, да, просто название глав возникло несколько типов колец. Там регулярное, то есть полное пересечение, вычисление. Я просто сказал, что каждое регулярное оно является полным пересечением. Каждое полное пересечение является значением. То есть, кто находится на классе чуть поменьше пересечения, что они чуть полное пересечение, именно 300 регулярное. Это как бы с точки зрения геометрии, часть многократности, особенность, локальное кольцо, локальное кольцо, плюс какая-то особенность, контролируется вычислительного пересечения. Ну, то есть, если мы входим в внешней геометрии, там можно встретить какую-нибудь условие, что типа рассмотрим схему, которая там локально полное пересечение. Это означает, что все локализация во всех точках полное пересечение. Или там рассмотрим многообразие, которое равно точек. Потому что там регуляция дальше формы, сегодня это кажется, что там рассмотрим многообразие полное пересечение. То есть это каждая локализация пересечения локальное кольцо, и там подтверждение не то, что локально illustris хорошо, а локально можно не локально illustris.
Понятно, спасибо.
Корыстно, к концу мы сможем технически охватить там, все либо.
Нет, вот как это воспроизводится с для условных категорий.
Поедешь на
ограничимся
3-4.
То есть, если посмотреть про классический текст трансформ на локальной плоскости, там как бы для коллективных это можно доказать для коллективных планов позже. А если доказать там для собственных, то там просто отдельная глава по локальному не могут, потому что это технический инструмент, что я чувствую, что я оказался. Даже мы скорее это тут. Вот, допустим, история глава техническая.
Что, слово проводили?
а локальная версия что?
Ну, да, это просто как локально были новыми, я
Колян Толкнулевич. Не было? А, ну они со Славой же коллеги. Чем ему провожать его? Встретиться?
Просто сейчас очень точно это объяснение.
Вот там уже говорилось про это.
Вот, что можно там 2 часа.
4 домашки, каждый 10 задач.
Да.
Ну, 10-15 решаешь, что по 10 задач каждый. Ну, пятерка.
Коллективный,
сервер для собственных механизмов.
Нет, в смысле, на если возможность посмотреть,
Если у вас если механизм коллективный, то получается, что коллективный получается частный случай, который имеется в виду.
Будешь ходить?
ну ладно.
А на
So let's continue and finish the proof of this theorem.
Отдохнуть.
So if we don't have any questions, I want to erase the proof and just keep the step 1. Maybe this is I can erase completely. And do step 2. Well, the step 2 is kind of independent. I can as well just done this step as the first step. And
Там пуля рядом с студенческим.
in this step 2, the claim is that without loss of generality, I can take this polynomial f that I have in this statement and replace this by another polynomial such that the condition in the theorem is replaced by the condition that when I compute this polynomial on the regular sequence, it's not just in some I to the t plus 1m, that's actually 0. Okay, so if we look at this condition that is given to us for the polynomial f,
Четыре штуки еще. Они ближе. И плюс.
this is again, the same reasoning that I was using in the step 1 tell us that this f computed on the regular sequence can be expressed as another polynomial. Again, let me call g. This is another step, and I can use this as independent notation. So this g has nothing to do with the previous g. So this is polynomial g, again depending on the regular sequence, and this is homogeneous of degree d plus 1. Okay? So if this is an element in this product, well, just think about what the elements here in this product are. These are exactly things that can be expressed by these polynomials.
Can you repeat? Why we can... Почему можем считать, что f равно нулю? F от x1, x2.
So this will abstract proof.
Ah,
This is the proof of this.
okay.
So this step 2 is to claim that the well, not this polynomial, but I can replace this by some other polynomial such that this condition is equivalent to this condition. Okay, so this is of degree d plus 1. So this means that I can maybe grab one more line here. So this means that I can write this g as the sum x by gi and the degree of the gi is again, notice the different form. This is just now just variables, the determinants, not the elements in the regular sequence. And just by definition, we set to be g tilde I to be the product of the xi and the gi, and finally g tilde is just the sum of this gi tilde. So just notation. Okay, let's look at the degree of the f minus g tilde. So what's the degree of this polynomial?
What's the difference between g tilde and g?
Well, it's kind of defined a different way. So g we obtain because we have this thing, then we introduce gi.
It's sum of xi, gi.
Yeah, so here this is the indeterminate, and this is the element of the regular sequence.
Ah, huh.
So what's the degree of this difference?
So degree of g tilde is d.
Yeah. So then this is the answer. The degree is d because degree of f was given as d, and now I replace one of the indeterminates by its values. So in some sense, it's kind of like taking this polynomial g and computing on the looking at this as a polynomial in the variable xn and plug in element xn instead of the variable. Okay, So the difference of these two polynomials is a polynomial of degree d. Now let's look at the difference and compute this difference on the regular sequence. Well, as we can easily verify, this is 0. So this is 0. So now notice that the coefficients of the polynomial g tilde are in IM.
Sorry, why degree of f minus g tilde is equal to g? Can it be less than g? F homogeneous polynomial.
Yeah. So that's not possible. Yeah. So what I want to say that the coefficients of the g tilde are in the IM, right? By the construction. If you just look at that, we have this xi's here. You'll see this. Now coefficients. So from this, it follows that the coefficients of the f are in IM, if and only if coefficients of the difference are in IM. And I claim that this finishes the proof of the step 2, right? Because now instead of the polynomial f, I can use the polynomial which is f minus g tilde, and the conclusion that the coefficients are in the IM, well, because the coefficients of the g tilde are in the IM, are equivalent for this polynomial f and the polynomial f minus g tilde. Okay, so this finishes step 2, and the last step is step 3. So we continue proving this theorem, prove this by induction, so we assume that this is true for n minus 1, and in the step 2 I want to show that this is true for n, and I need another induction. So step 3 is kind of the main proof, and here in this part we do the induction, one more induction, but now on d. So case so the case d equal to 0 is trivial, so we can assume that the d is positive. And let me write this polynomial as the sum of the g plus x and h. So here I assume that the g is in the m and depends on all the variables but the last one. So in other words, I just separate this homogeneous polynomial in all the powers that don't contain x and the rest. Okay, so when I plug in regular sequence and the polynomial f, I obtain 0. So this is by the step 2. So then it means that the g that I compute on the regular sequence plus x and h, again evaluated at the regular sequence. So this whole sum is 0. Yeah, but this is not n, this is n minus 1. So the last is n minus 1. Okay. Okay, so this polynomial f is a polynomial of the degree d. So this thing is something in the j to the dm, right? Now let's use step 1. So by step 1, polynomial h on the axis is in the j to the dm, which is of course something that sits inside I to the dm. Right, so I is obtained by just adding one more element xn. Okay? Do you agree with this claim that if I look at this formula, apply step 1, right, so then I'll get this.
Why is it so?
Well, we know that by this step 1 that this last xn is regular on any such quotient, right? So now we have element here in what we take a quotient by. So by the modulo g dm, we'll get this thing to be 0. Okay, so this will be our key formula that h is an element in this ideal, in this submodule. Okay, so by induction, coefficients of the h are in the IM, right? Because we constructed h. We constructed this h as the polynomial of degree d minus 1. And for d minus 1, we already know this theorem. Well, we assume by induction that we know this is for d minus 1. We try to prove this for d. So by induction, coefficients of h are in IM. But let's look at this formula one more time. So, I mean, this thing, this inclusion. We can say that h on the regular sequence is actually a polynomial. Let me call this polynomial little h. Again, depending on the elements in the regular sequence, but only up to n minus 1. So this is polynomial with values in module m, and depending on the axis up to n minus 1. So we're using this argument for the third time, that if something is in the product of some power of ideal in a module, then we can present this as a polynomial or some specific form. So this is also, let me say, this h is homogeneous of degree d. Okay, so as g plus xn, h, if I compute this on the regular sequence, then this will be the same thing as I compute f on this regular sequence, and I'll get 0.
Извините, а как все-таки аж маленькое устроено? То есть
Well, the existence of this little h follows from this thing. This is why I underline this. Since this is element here, I can write it in this form.
Там вот последний строчек мы должны представлять x1, xn минус 1 и x1 до xn.
Можем мы n-1 поставить, или просто...
Yeah, let's do this n minus 1. Okay, so by induction on n, now coefficients of the g plus xn little h are in Jm, but coefficients of the xn little h are in Im, which is quite a trivial observation. So coefficients, finally, coefficients of G are in Im. Well, and if the coefficients of G are in the Im, clearly the coefficients of F is also in the Im. So this finishes the proof. As you can see, this is not very homological, this very basic algebra, and this was done quite early. So I think if you open Russ's original paper, 1957, it's more or less the same book. But still, then people were not able to simplify this. Okay. Now let's look at the interpretation of this statement. So maybe, so can I try to keep the statement? Maybe it's too complicated. Maybe I just write something. Let's go to the associated graded. So I am assuming that you've seen this before. For example, when you discussed the dimensional theory for commutative rings. So whenever you have an ideal in the ring, you can consider the associated graded ring, which was, I hope, defined as the direct sum of the quotient of the ideal I to the k modulo I to the k plus 1. And of course the convention is that I to the 0 is R.
Excuse me, could you please repeat why coefficients of x and h are in Im?
This thing?
No, the next.
This thing?
Yes.
Well, we have it some here.
Okay.
So this is the associated graded ring. So this is associated with a ring and an ideal in this ring. And you can do this for the modules also. So Im direct sum for non-negative case IKM modulo IK plus 1M. Okay, now let I be an ideal generated by the regular signals. So I'll continue to use the same assumptions as in the theorem. So I'm just reinterpreting the theorem. So that's the regular signals on M. So we have a canonical surjection. We can take a polynomial algebra on N indeterminates and map this, of course, canonically to the associated graded ring. In the sense that, well, these are both graded rings, so in degree 0, you get, so here the degree 0 part is R, and here the degree 0 part of k is equal to 0, this will be R modulo I. So this will be just the canonical map to the quotient ring. And in the positive degrees, you take, say, degree positive, then the xi is mapped to the class of the xi. So this is in the I to the k modulo, no. But this is I modulo I squared. Even better, I can say this is not a positive degree, but this is just degree 1. And so this is a free commutative ring. The map is completely determined if I know what I do with the generators. So here are the generators, and let's just then send them to these classes. And of course, we have the same situation for the module. So let me call this map maybe psi. So this will be from the M to which I join n variables in the polynomial way, and there is a canonical map to the associated graded. Just so on this backward, I'm just introducing some notation for the objects and the maps that I'm going to use to reinterpret this here. Okay, so here, if I take a homogeneous polynomial of some degree, then I map this homogeneous polynomial to the homogeneous polynomial computed on the regular sequence. Right, so this will be in the IKM, and then consider plus of this thing. So in the IKM modulo IK plus 1. So this is what we do for our homogeneous elements, and then we just extend this by additivity. Okay, so there are a couple of trivial observations. I guess the first trivial observation is that if you look at the map psi, then psi is an epimorphism, or just epimorphisms of modules. Right? And the second observation is that if you look at the IM, x1 to xn, then clearly this sits inside the kernel of psi. Yeah, just look at this definition. So I'll get another map, let me call this phi. So this will be a map from the A modulo IM to which I adjoin polynomial variables, and I can identify this. If you, for example, go back to the definition of the M adjoint polynomial variables as a tensor product and use some basic properties of tensor product, you can see that you can identify this with the following quotient. You first adjoin polynomial variables to the module, and then take a quotient by the submodule of polynomials, but with coefficients in the IM. So let me leave this as a little exercise if this is not immediately clear, but it should be. So then this is a still map to the group IM. Okay. I claim that this last map is an isomorphism. Can you explain to me why this is an isomorphism? This is the kind of the key question. So, well, in other words, I'm asking you why the kernel of psi is exactly this thing. Yeah. The statement that this is an isomorphism is precisely the Riesz theorem. So, being this being isomorphism is equivalent to the Riesz theorem. So, in other words, well, you can kind of naively ask a different question. So, for example, you can look at the associated graded module, or even ring. So, you have a ring, you have an ideal, right? You choose some generators for this ideal, and you want to actually understand what's the associated graded. Can you do this? So, this theorem gives you an answer in the case where this is generated by the regular sequence. So, the associated graded is just polynomial ring. This is what we have here, right? The associated gradient will be polynomial ring. So if M is R, polynomial ring in n variables over the R modulo I, which is quite, well, natural to expect since the degree 0 component here is R moduli. But more generally, you can do this for any module. But as I mentioned, when you work with regular sequences, it's important to keep in mind the case that module is just the ring.
В каких ситуациях возникают эти ассоциированные коррелированные модели?
Well, I was hoping that you saw this, for example, in the basic commutative algebra course. You need this to prove the main theorem about the dimension.
Теоретические структуры выполнения параллельно возникают.
Не, ну,
So this is not a completion, this is a
Да,
раздутие там это возникает.
Yeah, in the geometry, this is related to the law algebra is a little bit different, but this is directly, well, if you think about this geometrically, Rick give you an affine scheme, ideal give you a closed subscheme. We can blow up this closed subscheme. This will be the approach of the Pavlov algebra, but the fiber of this ideal will be exactly the approach of this associated radius. This is geometric interpretation, but I want to finish my sentence about the dimension theory. If, for example, if you don't know dimension theory, you can learn it from Matthias Magdalena, and you'll find these things there, but without names. I think he uses notation something like R star, M star, some weird notation, but it's exactly the same things. So the idea is that in the dimension theory for Commutative rings, one of the ingredients is the somewhere function and somewhere polynomial, and this is quite similar to the Hilbert function, Hilbert polynomial in the graded case. You kind of start with the local case, you go to the associated graded, everything is graded, and there you have this theory of Hilbert functions, Hilbert polynomials. Yeah, and yeah. So and since this is geometrically an interesting question. So, for example, going back to geometry, you blow up something, and you want to understand the fiber over fiber over this closed subscheme, and you actually need some explicit description for this one. If for example, if you blow up, say, a point in the affine space, the point is just given by regular sequence x1 up to xn. So you can immediately see that the fiber over the point in the blow is the approach of the group, which is just the polynomial over field with n variables. So this kind of algebraic way to compute the fiber of the blow. Yeah, but I was trying to say that it's still, for different reasons, for geometrical reasons, for algebraic reasons, you sometimes want to understand what this thing is.
It's not the condition, it's the tangent component.
Yeah, I think this is true, but it's not really relevant for what it says. Yeah, so I was saying that there are some reasons, but you want to understand this associated objects, and the case of regular sequences is the simplest possible case. So there is nothing simpler from the point of view of this theorem. And of course, there are people want to understand this beyond the case of regular sequences, and there are, I think, hundreds, maybe thousands of papers about the structure of this module if this is not a regular sequence. There are even books. So there's a very famous book, Arithmetic of the Blow-up Algebras, which essentially tries to describe these objects which, when this is not a regular sequence. I is not a regular sequence. Okay, so finally I want to finish this first section with another definition. So let me call this condition star. So a sequence x1 xn is called M quasi regular if star is satisfied. So we can say that the Riesz theorem is actually telling us the following: any regular sequence is quasi-regular. Now, of course, there's a question, is it true in the other direction? And unfortunately, in general, this is not true, but you can see immediately that this cannot be true. Because, for example, being a regular sequence depends on the order, and being quasi-regular doesn't depend on the order. Order of the sequence. Okay. But we have the following theorem. The last theorem in the first section. So let Rm be a local Noetherian ring if the sequence x1, xn is m quasi-regular, then it is m regular. So in general, this is not true, that the any quasi-regular sequence is regular, but this is true for local Noetherian rings. In fact, if you look in the Musumura's book, he proved a little bit more general statement, not just for the local Noetherian rings. It will be one of the two important cases. Another important case would be a graded ring. But here we give a more general proof where you just consider the sequence of modules, m quotient by x1, m quotient by x1, x2, and all these modules has to be identically separated, but not to go on the technical details on the first lecture, so I decided to just prove this one special case. Okay. So first I'm going to prove that x1 is regular. So if x1 m is equal to 0, where m is some element in the module. So this is not g, this is the element. So then I can write m as an element in the IM. So in other words, so here, well, I continue to assume, of course, I is this ideal.
This is from quasi-regularity.
Yeah, this is exactly by quasi-regularity, and well, this is just the polynomial that we need to consider, variable x1 times m. So consider f being, say, m x1 m, doesn't matter. Okay, so I can write this m in this form. So then, if I look at the product of the x1 and m, I can rewrite this as a sum x1 xi times m, still summation over all I between y and 1 and m. And again, apply quasi-regularity, but now for this polynomial, where it replace elements by the variables. And then sorry, this is not m, this is mi. And then I will be able to say, again using quasi-regularity, that mi are in the IM. So then I do the same thing for the element not m but mi. So if I continue doing this, I'll get then the M is actually is in the intersection of the M to the K capital M. Okay, do you agree with this?
Not M to the K, but I to the K. Intersection of I to the K again.
Well, yeah, so this is the problem. M is also a maximal ideal, so I can,
So this I should be M,
well,
small m.
I can first write, of course, like this. This follows from what I will prove if I continue doing this. But in fact, I need what I wrote in the beginning, but this is of course not an element. This is a maximal ideal. So maybe this M, I don't know. Let's go with this M with a tilde everywhere. Not to confuse with the maximal ideal. Sorry for the unfortunate notation. And this is M, this is the maximal ideal. And of course I sits inside the maximal ideal, so this is not equal, but this is obtained. Okay? But what is the last intersection?
Zero by the articles.
No, Artin-Rees theorem is used in the proof, but usually it is called the Gross intersection theorem. So this is 0, and this statement is called Gross intersection theorem. So this is a fact that is usually proved in the basic course of commutative algebra, but if you for some reason don't know this and we want to learn this, Atiya McDonald, the last chapter of the dimension theory, contains a very short proof. Okay. So we proved that actually x1 is regular, right? We started with some x1 m tilde which is 0, and at the end we proved that m tilde is 0, so x1 is regular. So now let me say that m1 is the quotient of the m by the x1 m. So if we show that x2, x up to xn is m1 quasi-regular, then the result follows by induction. So it's enough to show that x2 xn is m1 quasi-regular. Okay, so let's prove this last statement. So let us take polynomial f in the m1 depending on the variables x2 xn. So this is homogeneous on degree d. Homogeneous of degree d. Such that on the regular sequence, and this starts with x2. This is 0. Now, so, and let capital F be a polynomial diffusions in M such that if you reduce this capital F modulo x1, you'll get little f. So little f is the capital F modulo x1 m. So we look at the polynomial that we have to consider, and we look at the lift of this polynomial from this quotient module to the module m with n minus 1 polynomial variables. Okay, so then if we look at this polynomial capital F, compute this on the regular sequence x2 up to xn. Well, this is of course not necessarily 0, but this is definitely of the form x1 times little m, where this little m, oh again, tilde, not to confuse this maximal ideal, is an element in the module m. Okay, so suppose this element lives in the I to the Lm. So m is filtered by the submodules
Yes.
m tilde. So suppose we can find this some L such that m belongs to this filtration term. So if we have this, well, L could be 0, very well. So there is not a problem. There is no restriction on L at the moment. So m tilde, if we have this as before, we can write this as some polynomial g, let's also indicate L in the notation, so GL, depending on the x1, xn. So here the GL is the polynomial with coefficients in module m in n variables, and this is homogeneous of degree L. So we can write f of the x2 xn as the x1 GL x1 to the xn. This is the same formula as before, but with the polynomial GL. Okay, so if
Why can't we suppose that m is the... Это мимолетность предполагаем или просто предполагаем?
well, at the moment I don't say anything about L, so I'm going to say about something about L after I do this argument. So it could be L is equal to 0. Right? It could be that you can choose L equal to 1, etc. But actually, if L is equal to 0, this can be the simplest case. Okay. So if L is less than d minus 1, then coefficients of the GL are in IM and IM and M tilde is in the I, the L plus 1M. Yes, so this is kind of high school statement. To understand this, well, you just need to look at this identity, right? And look at the corresponding coefficients, right? So you have some polynomial in this axis, and you have some coefficient, and you have polynomials in these variables and some coefficients, right? Now, this is of degree d, right? I wrote this, that this is of degree d somewhere.
We stated that f small of degree d.
Yeah, so and this is just the lifting of the coefficient. So yeah, so this is of degree d, and I assume explicitly that this is less of degree d.
Yeah.
So, for example, I don't know, if you take all the coefficients here, move this to the one side, left side, and you want the cancellation. And if you don't have this, then there's no way you get the cancellation.
So is coefficients of f is
This will be kind of in this axis of the degree. Yeah, so this will go of degree d, this will go degree definitely smaller than d. If you don't have any coefficients, at least at least one, maybe more than one pair of x's, then you won't be able to cancel this.
This is by regularity, by quasi-regularity.
This thing,
Yes.
I don't see how this is false from regularity. I think this is just by comparing the degrees.
But it is not equality of polynomials, it's in one point.
It's equality of values of polynomials.
Sure, but I think this is still enough. Again, think about this as a school statement about the algebra. So here you wrote some just the product, x2, xn, right? And you want to say that this is, and there is some coefficients, let's say m, right? And you know that on the right-hand side you have x1, and you have, say, just some one coefficient that depends on x1, xn. Now it doesn't really change much, but well, what I wanted to say is that I consider the monomial, which is just the product. Say the degree is right, so I can consider the product. No. Let me add some. Right, so if you want to get the cancellation property, then, well, since the degree of this thing is definitely smaller, then if you don't have any coefficients in M, you won't get any cancellation.
What is cancellation property in
I mean, the terms on the left and the terms on the right are the same.
Why?
Oh.
It's not polynomials, it's elements of M.
yes, so elements of m on the left and on the right is equal.
Yes.
Ну, короче, у тебя слева как бы сидит такая перемножение, которое лежит в и в степени dm. Да?
Мгм.
А справа у тебя будет сидеть x1 умножить на что-то, что сидит в степени меньше, чем, сидит в степени il. Вот, и если, а потом мы еще умножаем на коэффициенты какие-нибудь, чтобы вот это l получится.
Ну, мы как раз пользуемся
Именно
квазирегулярностью.
это x, а второй это x квадрат. X квадрат уже в первой степени.
Да, у меня тоже писал вычисление, возникло ощущение, что это как-то недостаточно.
Но это в точности квазирегулярность свойства. Но у нас получается, что x1 на GL от x1 xn лежит в и L плюс 1 m. А значит, коэффициенты многочлена лежат, поскольку он в степени... Короче, вот это значение, оно лежит в и dm, и в дэтой m. Или Ну да, справа у нас многочлен степени строго меньше, чем d. Поэтому его коэффициенты лежат в m.
Тут квазирегулярность для ничего.
У нас f это многочлен степени d, поэтому f от x2 xn лежит в idm.
Это правда.
А справа у нас многочлен ну, вот подставлено значение в многочлен степени L плюс 1, а L плюс 1 строго меньше, чем D. Поэтому по квазирегулярности его коэффициенты лежат в EM.
Да, я думаю, что это гораздо лучше. So, let me write this right here. Let's say regularity. Yeah. And I think this argument, you indeed have this argument with the elements and the firmness doesn't really work. Okay, but anyway, so the upshot is that the element M tilde is in the I L plus 1. So we can repeat this argument. So repeating the argument, we can increase this L by 1, and we can do this until we will get M tilde in the I to the D minus 1M. So this is where this argument no longer works. So now let's look again at the difference of the F minus x1 G with the index D minus 1. So when I compute this on the sequence x1 xn, so this is 0, and this polynomial f minus x1 g d minus 1 is homogeneous of degree d. Degree d. So coefficients of f minus x1 g d minus 1 are in the IM, and since x1 does not appear in F, coefficients of the F are in IM, so coefficients of the F are in IM1. And this is all we need for the proof. Okay, so this is the last such statement about the polynomials. So I want to say that this theorem, which is a little bit easier, but this kind of exception of this course. There won't be any proofs like this in this course. So this is kind of the beginning. Basic properties of regular sequences. The rest is more or less homological. We go to write some complexes, compute extents, etc. But yeah, we've had such proofs in the very first section of the very first chapter. Okay.
Вот то, что мы здесь исходно считали, что f от x2 равно нулю, это аналогично, как было в шаге 2 в доказательстве теоремы.
Да. Okay. So I don't want to give you a wrong impression about this course, so let me try to prove at least one here that is not that, which is not just the proof about polynomials. So in the second section there. Okay. So here we have following theorem. So R is the theorem, right? So theorem, right? M is the finite R module with we assume that IM is not equal to M. And we also assume that we have some number n which is greater than 0.
It's just an arbitrary.
Yes. I is an ideal. Say I is an ideal in the group. So the following I will it. So the first property is that the xi between n and m is equal to 0 for any I less than n. N is just some fixed number. And for any finite module n satisfying additional condition, then the support of n is equal to the vanishing set of I. Condition 2 is just a special case. xi between R module I and M is equal to 0. And this is for any I less than n as before. So I just choose n to be R module I. Clearly this condition is satisfied. Now 3. More special case, xi between n and m is equal to 0 for any I less than n, and some finite R module n such that the support of n is equal to the vanishing set of I. And finally, condition 4, there is
Between third and fourth.
between what?
What's the difference between third and first?
Well, the difference is this is for any, and this is the
The
this
sum.
is-
Okay, thanks.
Yeah, so the last statement is that there is an M sequence of lengths n in the ideal. So here we can see that the existence of empirical sequence controls the vanishing of the x. Of course, many of these kind of four equivalent conditions, we need to prove four conditions. Two of them are completely trivial. So, of course, one immediately implies 2, and 2 immediately implies 3. So this is clear, just in special cases. But that 3 implies 4 is less obvious. Okay. So I want to show that there is a M sequence of length n. Or suppose that there are no regular elements. If I consists of 0 divisors, right, so there are no regular elements on the M. So then I can write that I is a subset in the set of all 0 divisors. So this is notation for the 0 divisors of the module M. Well, now I need another fact from the basic algebra. I hope that you know this, that you can express 0 divisors for a finite module or a Noetherian ring as the union of all associated primes. Have you seen this before?
Can you remind what is associated primes?
Okay, but maybe I'll do this on the other whiteboard. So P is the associated prime with the module M. This means that there is an element, say little m, in the M, such that this P is precisely the annihilator of this element little m. So geometrically speaking, if you think about schemes, then we have a fine scheme. This will be some coherent sheaf, and this coherent sheaf is supposed to have a section vanishing precisely at the irreducible subvariety given by P. And you can also think about this as a kind of high-dimensional generalization of the notion of the eigenvalue of a matrix. Okay, but of course the equivalent way to say this is to say that there is a exact sequence like this. Right, this is just take one in the R, map this to the element M, and the kernel is precisely P, since this is the annihilator. But what I want to say is that this one line is not enough. So if you want to follow proofs, like in this theorem, you need to know some commutative algebra. For example, you need to know something about associated ideals. So it is not in the Atiema Donner, but it is definitely covered in the Musuru's book, in one of the first chapters. Maybe if you find this helpful, I have my own notes on commutative algebra. Well, when I teach commutative algebra, I follow those notes. It's quite short, it's only 50 pages. And I think about associated primes, maybe 5 pages or something like this. So maybe on the work class I can post these notes, and you can briefly review what you need. For example, about the associated primes. Yeah, so this ideal is in the union of the associated primes, and moreover, it's the fact that we need to know that the number of associated primes when the ring is not even and the module is finite, then this is finite. Now, I claim that the I is actually a subideal in some P, where P is some associated prime of M. Why that is true?
Since it's consistent union.
Yeah, but if this ideal is just a subset in the union, how do you conclude that this is a subset in one individual prime ideal?
Like prime avoidance.
Yeah, exactly. So this statement is the prime avoidance. So another statement that you can look up, say in Musuru's book or in my notes if you're doing the book class. Okay, so by prime avoidance we have this. Now let's look at the exact sequence that I already mentioned on the other whiteboard. So we have our module P. This is mapped injectively into the module M. And now I can localize this at the prime ideal P. Well, localization is an exact factor. So this is what I'll get. And of course, again, using the localization is exact, I can as well rewrite this as this quotient, and here we have localization of M. Let's, just for shortness of the notation, set K to be the residue field at the prime ideal P. So this is RP modulo P RP. So in the good notation it would be K that depends on P, but here we have only one P. Okay, so P is in the vanishing set of the ideal I, so meaning that I is contained in P. Well, that's we already know. And since we work under the assumption 3, we know that the vanishing set of the I is precisely the same thing as the support of N. So this implies that the localization NP is not isomorphic to 0. And by Nakayama's lemma, Nakayama's lemma, I claim that the tensor product with K is also not 0. Now, for local rings, it would be exactly statement that this is 0, then this NP is also 0. Or I can as well write NP RP. Maybe I keep both. So, we have a non-zero finite dimensional vector space. Non-zero finite dimensional vector space. Hence, the dual vector space is also non-zero. So, Hom over K and tensor with K to the K is non-zero. There is at least one linear form. And now we'll look at the composition. We have NP. This is mapped, well, this is mapped to the N tensor K. Well, maybe the way I explained it is not very clear why there is a map such like this, but I can also identify this using the exactness of the localization with the NP. In this case, it's even easier, just using essentially the definition of K, I can identify this with the NP modulo P NP. Hence, from the NP, I have a just canonical map to this quotient. Okay, so here I'll get the map to the K. Well, this is L, which is not equal to 0. And finally, from the K, I have a map to the MP, which we already constructed here. So this is the same map. So I constructed 3 non-zero maps, and I look at the composition. And if you look at the composition, you more or less can immediately understand that this composition is still non-zero. So I can claim that this composition is the Hom over RP NP MP. The last thing can be identified with the localization of the Hom over R between N and M, and then I localize at P. Recall that that the Homs not always commute with the localizations, but they commute, for example, if this is a finitely presented module, but in our case we have Noetherian ring and a finite module, so this is finitely presented. Okay, so we'll construct a non-zero element in such localization. Hence, this module before the localization, sorry, this is N. And M. So this module before the localization is not 0. And if this is 0, then the localization has to be 0. Okay. Okay, so this is non-zero. Yeah, and so this is non-zero. And we notice that the Hom is just the special case in the statement 3 when I is equal to 0. Right? So if we assume that there are no regular elements, sort of by contradiction, then we will get that Hom here is not 0, which is a contradiction.
В таком случае, что Хом
не нулевой?
Well, because we have the localization of home is not zero. And that is because we construct an element which is a composition of these three maps, which is not zero. I didn't prove that this is not, that this composition of three maps is not zero, but it's not very hard. Because all the maps given here are explicitly given. This is just the embedding, and this is just some linear form, and this is canonical subjection.
Можете повторить аргумент, который вы говорили, что локализация home это home локализованного?
Well, I was saying that in general, if you just have two modules, you take localization of the home, it's not true that you can move this localization inside here, 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 but it is true if the first argument is finally presented module. And this, in this case, this works because the ring is Noetherian, module is finally generated, hence it's finally presented. This is another that you can find in my notes on commutative algebra if you don't know this.
What is finally presented?
Finally, what's finally generates? It means that you have finally many generators, and finally presented means that you have finally many relations among these generators. So it's a more restrictive notion. Over Noetherian rings, this is the same thing. There is no difference. But over general ring, well, it's two different notions.
Okay.
So yeah, we like didn't prove 4.
We didn't prove 4, unfortunately, we are out of time. But maybe, let me maybe just use for three more minutes. I think I can finish this proof in 3 minutes. Okay, so we can conclude from obtaining this contradiction that I contains M regular element X. So this means that when n is equal to 1, we done, right? But if n is not equal to 1, we need to do one more thing. And this is the standard kind of, so n is positive, standard kind of induction in this theory. You look at the short exact sequence, where you have m multiplication on x, m, and then the m1, which is the same thing as, of course, as the reduction modulo x. And then you look at the long exact sequence of x, you'll get xi between n and m, again xi, again n and m, xi, n m1. So then the next term will be xi plus 1, n, m, etc. It just repeat itself. And the previous term is xi minus 1, n, m. Sorry, this is nm or nm? nm1. Yeah. So this long exact sequence for the x. And so by induction, I contains an M1 sequence x2, xn. But if this is the case, then we actually prove that we prove that 3 implies 4. So next time we're going to show, we're going to start with that 4 implies 1. And from this observation, well, we will derive another risk theorem, and another risk theorem will tell us that the notion of the less maximal regular sequence is a well-defined notion. It doesn't depend on the sequence. Any maximal have the same number of elements, and this will be precisely the notion of this. Okay. But the point of the last proof was that this is kind of typical proof for this course. They prove for the first free stream, and the theorem after that was not very difficult. This computation is polynomials is the only place where you can see this in this course. But the computations with associated primes, prime avoidance, localizing short exact sequences, and localizing homes, etc. This is kind of what we're going to do in this course.
Такой же,